of why these capacities so damn low, and it is a very understandable frustration. In addition to this, there is without a doubt a spectrum of understanding behind what these capacities actually represent in the industry. I vividly remember being a grad at Becker when I came out of university and designing using C2 capacities. And if I'm being honest, if someone had asked me at the time why I was using a C2 capacity, my answer would have been something along the lines of because it is the seismic capacity of an anchor in cracked concrete. How we got here. So these are images from the 1994 Northridge earthquake in California. Actually a very large earthquake. So the PGA in the highest acceleration area was about 1.8 G, which when we compare it to what Christchurch was, which is about 1 G, pretty drastic kind of event. But believe it or not, prior to this, the industry was using monotonic capacities in uncracked concrete to design post-installed anchors in concrete, which I suspect we can all intuit isn't going to be appropriate for a lot of the design that we're doing for post-installed anchors in seismic regions in concrete. And as a result, there was pretty widespread failures of anchors among many other things, which is to some degree understandable in an event this size. But the anchors was really a highlight, or at least one of the highlights that came out of this earthquake in terms of learnings. So much so that actually the US banned post-installed anchors completely in seismic applications for the best part of 2 years. We start having cracks in our concrete and our anchors are in those cracks. That's obviously going to impact the performance of any post-installed anchor. Take the extreme case where your crack starts becoming wider than your anchor is going to fall out of the hole. Thankfully, we don't often have that scenario, but it's a spectrum, right? The larger the crack, the more impact we have. But there is this baseline assumption when we talk about this that we are allowing for when cracking occurs in concrete, that crack will occur where that anchor is. And this wasn't just good judgment. This was actually based on a research program that was done in California in the 2000s. I've got a screenshot for one of the test results there. The idea behind this, and it was one of the test programs that was trying to build the data that was required to build these test programs for anchors. But what that was looking at is what is the probability that when we get cracking occurring in concrete, that crack occurs where our post-installed anchors are. And the key takeaway is that it's very, very likely, much above random. And this makes a lot of sense. We have a very homogeneous or reasonably homogeneous material. If we put an anchor into it, it acts as a stress raise. And then when we start getting cracking occurring in these concrete units, which we do even under just surface loads, right, but definitely under kind of design level loading, because we have a stress raise there, there's a very, very good chance that crack occurs where the anchor is. And so the baseline assumption is that if we're putting an anchor into concrete or reinforced concrete, we are assuming that when cracking occurs, that cracking is going to happen where that anchor is. And that's a pretty reasonable assumption in my mind. Because we have this baseline assumption that our anchor is in the crack, that means these cracks are going to open and close around our anchors. And this obviously is going to have an impact on how the anchor behaves. And so what a C2 capacity is trying to represent is the impact of these three mechanisms and a crack width up to 0.8 mils wide. Now, when we were doing this testing, we started playing around in our own lab with some of the variables. We wanted to understand what the sensitivity of these variables were, because you get some test programs where your variable is set as a number and you could increase it and decrease it, and it's not that sensitive and it doesn't really have a big impact on the outcome. So we wanted to understand the kind of how sensitive these variables were to the end result we were getting. And so we played around with it a little bit, and the conclusion was they're incredibly sensitive. And the two variables that we care about here are the crack width, so that 0.8 mils, and the number of cycles that we're putting the crack cycle test through. If you have a crack width that's a little bit more than 0.8 mils, you get a significant reduction in capacity. If it's a little bit less than 0.8 mils, you get a significant increase in capacity. And similarly for the number of cycles, especially at maximum crack width, if you add more cycles to that test, your capacity drops. This 0.8 mil crack width apparently has been developed for reinforced concrete beams. It's not immediately obvious to me that translates perfectly well to other elements in a reinforced concrete structure. Maybe it does, not sure. From a design point of view, I think the really important thing to keep in mind is that if you're using a C2 capacity, what you actually are allowing for is a crack width up to 0.8 mils. If for whatever reason you're expecting cracks larger than that, the C2 capacity is probably not very appropriate. It's probably actually overrating the capacity. Similarly, if you're expecting cracks less than that, then your capacity is going to be quite conservative. And one of the reasons we started playing around in the lab, trying to figure out how sensitive things like crack widths were to the end result, is because we wanted to understand how much this matters. And it's really sensitive. Like the outcome really matters on what your crack width is. And so it's a really important thing as a designer to be aware of, that when you use these values, that is what you're allowing for. And that's what's been tested. Reasonably precise answer would be that a C2 capacity is the expected 5th percentile capacity of a post-installed anchor in a reinforced concrete beam just outside of the plastic hinge zone in a crack that is 0.8 mils wide in a 90th percentile 475-year return period earthquake in Los Angeles. Which is quite a specific thing. Aware of what specifically that value really represents is useful and can be kind of accounted for a little bit in design to adjust how you're using and how you're designing with post-installed anchors. And it's really important that when we're building assessment criteria, that they exist to support the designer in that goal rather than helping suppliers differentiate products. But I think being